In this demo, we demonstrate how users with basic background in one of these workflow management systems can use common framework and switch between them. However, for this demo, we run the generated code using VFG's Executor without any additional effort, but we do not claim that the generated code for every application will be executed without additional code modification. This is because of high-level abstraction layer during the code generation phase that ensures portability between different workflow management systems at the cost of additional manual configuration for a specific application development, scaling from local to supercomputers. Later, this will be more clear with motion detection example at the last part of this hands-on. We start again with setting up our workspace and continue with code generation for random task graph using both task and parser models. Thanks to VFGs, the procedure is almost the same, and we should just set up our working space, then go to the navigation phase, select our configuration file, set our input path, and generate different models for both path, task, and parser separately. As you can see, the model is generated for task and also the graph. We just switch to the parcel and then generate the code for parcel in different folder and different file, and you can just navigate to the printed path on the console in order to have better look into the generated files. We can also use the embedded editor to see and edit the files, Python files or YAM or JSON files. This is a generated file for task. Well, we also can switch to the other file for parcel in a few seconds, and in order to have a better look and insight on parcel generated code by VFGs. However, the embedded editor is not powerful as common editors used in IDEs such as Eclipse or Visual Studio Code, but it enables users to address basic file editing needs during workflow integration. For running the generated model, we should switch to Executor window and choose Task or Parcel Executor. Afterwards, we should select the Python model, and for the input section, if we are using the local executor, we must select only one input path, which is also used as a launch directory. In the case of local executor, all necessary inputs during runtime should be placed in the same folder. Since in this example we do not use any data, we only use multi-thread executor. As it is printed on the console, there are some missing Python files, and that those modules cannot be found. In this case, my function module cannot be found in this demo. And just to resolve this issue, we select the Python module on the local disk, and this path will be inserted into the Python path automatically by VFGs. In fact, VFGs update Python path just before running the Python model. In the case of SLM that we will see in few minutes, these Python files will be transferred to remote machine automatically, and also the Python path will be updated by VFGs in order to ease users running the model on local computers, local machine, or supercomputers. As it is shown in this demo, we can just easily switch to parcel model and run the model, and again there are some missing packages. This time we choose them, and the path will be inserted to the model automatically, and after the computation time is passed, you can have the result which is printed on the console. In order to submit job remotely, you should enable SSH passwordless login and then run Jupyter Lab. There are plenty of good hands-on available on internet and how to add your key to SSH agent and enable SSH key. We briefly just do it here. In order to enable SSH passwordless login, we add our key to the agent and then log into remote machine, enter our one-time password and then our password to the SSH key in order to enable passwordless SSH login. Additionally, you should also consider the additional authentication methods and requirements of supercomputer centers. For example, some of them force users to register the public key on the web portal instead of using SSH copy ID. As you can see now, the passwordless SSH login is enabled and you can just run Jupyter Lab and continue with the demo and submitting job remotely on the supercomputer. Here again, we select our working directory, set our working directory and continue with selecting our model, inputs and necessary modules. That interestingly, VFGenes will build a file system on remote machine with lib folder and all necessary inputs and update Python path in order to just run the model using these push buttons as we see in few seconds. And we can also use this command text area in order to issue any pre-launch command, and then we just set our hostname, username, and through the resource pane we just set and specify the amount of resources. We use sinfo command to get the available partition name from Slurm. In our cases, we use dev single, which is a single node partition and is proper for development and just testing your model or your code on one node. And we just ask for half an hour because since this test will take just around 1 minute, 2 minutes. And we just proceed to submit our job on supercomputer, which is the remote one. And here we just also set the launch directory. We extend only the home directory with a custom name in order to have a unique launch directory on remote machines. Again, this folder will be created automatically by pressing the run button, and the file system including the lib folder and all inputs will be created automatically on remote machine in order to ease user for running and executing their computation on supercomputer. Here we just run the model and see the my function module is copied into the remote machine using rsync under the hood, and then we see the job is submitted to the machine and it is waiting for resources. After waiting for the queue time and computation time, the computation is finished and the underlying code is executed on supercomputers. This is the SBatch file and content printed out on the console. Additionally, we can navigate to the launch directory and see which files are created by Dask workflow management systems, and see if we can use the submission file and output generated by Slurms in order to debug and do further monitoring. In the same way, we just switch the model from Dask to the parcel and add additional necessary module, if any, in order to be transferred to the remote machine. Additionally, we also should update our launch directory. Since we switch from Dask to parcel, it is recommended to modify the launch directory in order to create a unique launch directory for this model, which is different. We just delete the Dask and add a parcel and run the model. As you can see, again the model is executed on the remote machine. Files are transferred to unique file the launch directory, and we just check this queue, we wait for the job, and the job is again finished on the supercomputer. And we also can go navigate to the launch directory and see which files are created by parcel workflow management systems, and which information and which files are created by parcel workflow management systems. As we covered in this demo, we suggest how generated a model by VFGenes can be submitted on remote cluster using our local working station. And also we can just log into the remote machines and check and navigate to the launch directory for additional generated output files and information and data by the script, Dask and parcel, and also Slurm workload manager. More or less, we covered all necessary topics for this demo. Thank you for watching, and please contact us for further inquiries.